Hi students, we're going to use logs to solve exponential equations. The big thing here is being able to convert back and forth between logs and exponentials. The first one we're going to look at is one that you should have seen way back in Algebra 1 type stuff. And we're going to look at this with regards to a common base first. Because it's possible for me to write this as 2 to the third instead of 8. We got x minus 2. And 4 is the same as saying 2 squared. Then we got x plus 1. And when I have the same base, that means that those sides of the exponents must be equal as well. So 3 times x minus 2 and 2 times x plus 1. Solving this, 3x minus 6 is equal to 2x plus 2. Getting x by itself, we're going to have 1x on this side and 8 on this side. With logarithms, we don't really have a good way to do this yet. We will, but we don't have a way to kind of deal with the fact that these are exponents on both sides and we don't have log properties to work with yet. Solving this graphically is going to be a big mess, so we're going to kind of avoid that for now. But if you have Desmos open, you want to graph each of these, you're looking for their intersections. So you're going to have two equations that end up looking something like this, and wherever they intersect is going to be the x solution to this. All right, so now we have some kind of a reason to use logs, because I don't have a clean number that if I wrote this as 3 to something, I could turn this into 4. So we really don't have another path. Looking at this, I'm going to convert this to log form. So I'm going to have log base 3, okay, that's my base, of 4, that's my argument, is equal to my exponent, and I actually just solved that. This is the exact value for x. You can get a decimal approximation for this very easily with a calculator. We used to use tables for this before calculators were common. But at this point, your problem is done. For the next one, I'd like you to take a look at this before we try to solve this. Because if I've got 5 times 5 times 5 some number of times, there's no way that I could ever get this to be a negative value. So this is one that would have no solution. If we think about this graphically, we have an exponential that has an asymptote at 0. We want to find where this is negative 2, and this graph never goes to negative 2. All right, here we've got ones that have a couple steps for us to work with. First, my big goal is always to get the weird thing by itself. So if we've got 2 times 5 to the x plus 2, I'm going to divide both sides by 2. So I get 5 to the x plus 2 is equal to 7 halves. Now I'm going to convert. So we've got log base 5 of 7 halves is equal to x plus 2. I'm going to minus 2 to both sides. I can't combine those. So we get log base 5 of 7 over 2. And then just minus 2 at the end is equal to x. That's the end of that problem. For the other one, I'm going to convert this to logs because we already have that expression by itself. This is going to be log base 2/5 of 1/3 is equal to x minus 3. And to get a final answer, we've got log base 2/5 of 1/3 plus 3 is equal to x. There's nothing to combine, so we are done at that. We can do the same thing going backwards with logs. This is log base 10. So I'm going to minus 5 to both sides. We got 3 log base 10 of x is going to be 3. Divide by 3. We get log base 10 of x is going to be 1. Converting, base 10 to the first power is equal to x. That means that 10 is x. All right, looking at the next one, this is kind of interesting. So I've got a log base 5 on both sides. I feel like there's some stuff I can work with there. There's a little bit of a complication because I've got a 2 out front. And I'm actually going to, for now, since we haven't talked about log properties, just change this problem to be a little bit simpler for us. So we've got log base 5 of 3 is equal to log base 5 of x plus 1. The only way this can work is if the insides are the same as well. So 3 is equal to x plus 1. Therefore, 2 is equal to x, and that's it. Similarly, for the first number c on this page, we've got the same base log on both sides. So we're going to have x minus 2 is equal to 3x plus 2. I'm going to get my x in the same side to get 2x. Bring my positive 2 to the other side to get minus 4. We get x is equal to negative 2. Here we have to be a little bit careful because sometimes log equations give us answers that don't work. And if we have log base 3 of negative 2 minus 2 is negative 4, we have a problem because we end up with this weird expression. 3 to the exponent is negative 4. We talked about you can't do that. There's no positive number that you can multiply by itself and ever end up at a negative answer. This would be called an extraneous solution. So I'm just going to write no solution. Extraneous means a solution that we get algebraically, but does not work when we try it. For the other number, c, we're going to start by dividing both sides by 3 to get log base 2 of x is equal to 4. Now I'm going to convert base 2 to the 4th power is equal to x. 2 to the 4th is 16, and that is our final answer. We don't have to worry about extraneous solutions there because that's not a negative. It's only when you have negatives on the inside of logs or 0 on the inside of a log that we have issues. Looking at this one, we don't actually have enough math to solve this quite yet, so we're going to hold off on this.